In this video, we will be solving two end of chapter problems for chapter 3 on quality management. The first problem we're going to solve is about making a P chart with some data given, and the second problem we're going to solve is about calculating process capability metrics, CP and CPK, also with some data, some measurements about the process given to us. Now, these questions are slightly different from the solved examples in the textbook. The main difference is that in these problems, you're given raw data, how data is collected in real life, and then you have to find the sample statistics like P bar or like the long run average X bar. Whereas in the solved examples in the book, often the statistics are already given to you. So you're already given P bar, or if you're not given P bar, you're given like the sum over a number of samples, and it's kind of easy to calculate P bar. Especially for the CPK question, you're often given, the average of the process and the standard deviation. You don't have to calculate these metrics or some of them, right? Now, this change should not make much of a difference, because students who are studying operations management are supposed to know how to calculate simple descriptive statistics of a sample. Students should know how to calculate the average or the mean, how to calculate the standard deviation, and so that's all that's required, right? However, I do understand that some students have taken statistics in the distant past, and so they may need a refresher. Hence, I'm going to show students, I'm going to show you how to solve these problems in this video. Let's look at the first problem. So in this problem, we have some data from a hospital, and we are asked to make a P chart. The question telling us to make a P chart makes things a little bit easy for us. We should be able to figure out what type of chart is required. So even if the question just said, give me the upper control limit and the lower control limit of the relevant chart, and you have to figure out whether to use a P chart or C chart or X bar chart, so on, that is completely valid. You should know how to figure out which type of chart to use. The lecture provided to you does cover that. When discussing any type of chart, it tells you where this type of chart is used or when this is used, and so that you should know. Let's quickly review that. So the key to determining what type of chart to use, it depends on the data given and how what a sample is for this data. So a hospital administrator has taken random samples of 64 employees every day. So each day is a new sample of 64 employees. Then once the sample is taken, the administrator goes through the sample, and for each employee, it is determined whether the employee is present or absent, right? And then you add up how many people from that sample of 64 were absent. So the data that is being shown here, you can see that on the first day where we took the first sample, only one person out of 64 was absent. On day 2, 2 people were absent. Day 3, with the third sample, 5 people were absent. And so the purpose of taking these random samples again and again and finding how many people are absent is to get some handle on absenteeism, like how often are people absent. Okay, so we can see that each sample is comprised of multiple people, 64 people in this case. So we have a sample size of 64, right? So we can write here that our sample size is 64. And then for each person or thing inside the sample, we have only 2 possible outcomes. Either they came to work, so they're present, or they're absent. Okay, and we count how many were absent, and that is reported in this table. Okay. So given this description of how the data was collected, the underlying data is yes/no data, right? Or 1-0 data. So we code present as 0, absent as 1, so we can sum up the column to get how many people were absent. Whenever you have yes, no, good, bad, present, absent data with just two possibilities, and then you may summarize the data over the sample. So the count is doing the summary. That's fine. You can summarize the data, but the raw data has only two levels. This is sometimes called binary data. Okay, binary, B-A-N-A-R-Y, binary data. And for binary data, we always need to use the p-chart. So just by the description of what the data is, I can determine that I need to use the p-chart. Okay, and the slides also talk about this. Let me just show you this slide for the p-chart. Okay, so you can if you look at the slides tell you that each unit that is observed can be placed into two categories: good or bad, pass or fail, yes, no, 1-0. And so when you have data like that, each unit within the sample can be assigned one of two levels. Then you'll use a p-chart. Okay, so we know we're going to use a p-chart here. Now, to get the data into Excel to actually make the p-chart, we can click this button and copy the data by Control-C or Command-C, depending on using Windows or Mac, and lo and behold, we have the data. Now, this data is actually, you have all of these columns because the data is in wide format. It's been moved around so that originally the data was like this, right? Just two columns, day and how many people are absent. But it was moved around to the right so that it doesn't go vertically too much, and you can put it on the screen and you can see all of the data on the screen like this in one go. Okay, it doesn't matter whether you put it into two columns like that or not. You could leave it, you could leave it like it was. It doesn't really matter. Because what you'll need to do is you'll need to find the average of this column, and you can find the average of the data whether it's in two columns or one column. But just for I like to see data like this because I think it's a little bit easier to enter the formulas when all the data is in one column vertically like this. So how do we calculate the p-chart? Okay, for p-chart we need p-bar, which is the average proportion. And then we need the standard deviation of p-bar, which depends on the sample size. And then once we have the z-score as well, we can calculate the control chart. So we need to compute like 3 or 4 things. So we need to know, p-bar. Okay. Now each sample actually has a proportion p. So P1, P-SFI just means P1. For day 1 you have P1, day 2 you have P2. What are the different proportions for each day? Because my sample size is 64, if I divide the number of people absent, okay, by 64, and I'm going to put dollar signs around this cell. So if I drag the formula down, this cell, red cell, is locked and it doesn't move because there's nothing below 64. So you can see here that the proportion of people absent, okay, on the first day is 0.015. You can also read it as 1.5% because a proportion goes from 0 to 1, whereas a percentage goes from 0 to 100. So multiplying a proportion by 100 gives you the percentage. I can calculate the proportion for each sample, right? And you can see some days there's a higher proportion. So this day about 9.38% people were absent. This day is even worse, about 14% people were absent. but then some days are relatively good, like the first 2 days, 1.5 or 3% people absent, so small proportions here, right? Now P bar is the average of all of these proportions. So you can find the proportion for each sample and then calculate the average. If you just select these values, Excel will show you the average here. If it doesn't show you the average, right click here and then you can choose which statistics to show you from the menu that appears, right? Now this is not the way the slides show you. The slides show you a little bit faster way. So I will show you that as well. So I'm just going to find the average of these just to show you that this will going to give you the same answer as this formula on the slides. So the formula on the slide says find the total number, the total count. Okay, defectives, we have absentees. So, we are going to replace defectives by number absent. And you divide the total number absent over all the samples by the sample size multiplied by the number of samples. So using the formula on the slides, we'll take the sum of all of the absent counts, and then we'll divide that by the sample size, which is 64, okay? And then we have to multiply it by the number of samples. So how many samples did we take? Well, day 1 was 1 sample, day 2 was another sample, day 3 was another sample. So we have 15 samples. So multiply by 15, okay? And you can see that the P bar you get from the formula given on the slides is exactly the same value as if you found the P for each, the proportion for each sample, and just took the average of those proportions. So both ways give you the same answer, okay? Then we're going to need sigma of P bar, okay, which is the standard deviation, right? Because if you look at it, if you were to take new samples, you'll get a different value of P bar because you can see day to day there's variation in the proportion absent. So that's why we have the sigma P bar. And if you don't understand why you need sigma P bar, it has to do with probability that the stats course is supposed to cover, and I can't teach you, everything in the stats course again. But the basic idea is you got this value of P bar with these 15 days of data. If you were to pick a different 15 days, you may get a different value of P bar. And so the value of P bar is going to move around. How much it move around is estimated by the sigma of P bar, okay? Because the true value may not be 0.069. It may, because this, the days we picked may have given us 0.069, but had we picked some other days, we may have gotten like 0.063 or 0.07, right? And so we need to estimate how much can P bar move around. So that's given by sigma P bar, and we have the formula here. It's very simple. You take P bar, you multiply it by 1 minus the P bar, you divide by the sample size, and you take the square root. Now, a very common mistake at this stage is that people don't know what is n. Like, what is the difference between number of samples and the sample size, okay? So just to clarify, let's put number of samples 15 here. And instead of hard coding 15 in this formula, I should select 15 here, okay? Okay, so sample size versus number of samples. Number of samples, each row in the data gives you, in this case, is giving you data about 1 sample. But, 1 person absent doesn't mean you just measured 1 person. You actually measured 64 people, right? So the sample size is how many things or people are within each sample that you take. And the number of samples is how many times you repeat that activity. So you repeat it 15 times. Okay? So sigma P bar is going to use the n value, right? It's not going to use the number of samples. So we are going to be using this one in the sigma P bar formula. So we're going to do square root. So SQRT in Excel is square root. Then we take P bar multiplied by 1 minus P bar. The asterisk symbol is just multiplication. And then we divide this by the sample size, which is 64, not the 15. That's very important. And then we close parentheses or brackets, and here we get 0.03185 sigma P bar. Okay. So if you look at the upper and lower control limit formulas, we know P bar, we know sigma of P bar, how much is the variability in P bar, right? And we know sample size n, that's what we use to calculate sigma P bar. The only thing we need to know is Z, okay? So Z is sometimes very straightforward. If the question said, make 3 sigma control charts, then Z is simply 3. Z is just 3, right? If the question said, make 2 sigma control charts, Z is 2. If the question says, make 4 sigma control charts, Z is 4. Okay? This question does something a little bit more fun. So this question does a little bit more fun by telling you what is the probability of type 1 error you're willing to live with. So, the slide's going to talk about type 1 and type 2 error. And so you can look up the concepts here in the relevant slides, okay? So I'm not going, because I already explained that in my lecture, I'm not going to re-explain that concept here. But what I will show you is how do we go from type 1 error to a z-value, okay? So if your type 1 error probability, that's often referred to as alpha. So let's call it alpha. So alpha is 1% for us, right? So in this example, alpha equals 0.01. Why 0.01? Because a probability of 0.01 corresponds to 1%. This corresponds to 1%. Because 1% is like 1 out of 100, which is 0.01. Okay. So type 1 error of alpha means that in the normal probability distribution, you split up the alpha into 2 parts, and you put alpha over 2, half of alpha probability in the right tail, and you put the other half alpha over 2 probability in the left tail. So if you add up the tails, if you add up this and this tail, you get alpha over 2 plus alpha over 2 equals alpha. So your type 1 error probability is the area in the 2 tails. And if the total area has to be alpha, then each tail is going to have area of alpha over 2, so it can sum to alpha. Okay. So if the 2 tails have area alpha over 2, each has alpha over 2, then what's the area in the middle in this region right here? Well, total probability is always 1. So this area right here is just 1 minus alpha. Okay. So we want to find the z-score corresponding to this value here, okay, the z-value here, such that that the probability to the left of z, so the probability to the right of z is alpha over 2. So what is the probability to the left of z all the way to the end? Well, that's just 1 minus alpha over 2. Okay, well, how did we get this? Well, the white area here is 1 minus alpha, and then you have to add alpha over 2 to it. So if you do 1 minus alpha plus alpha over 2, that's simply 1 minus alpha over 2. So that is the probability to the left of z. Okay, if this looks complicated, don't worry. It's a lot easier when you have the actual number. So let's do this with actual 1%. Okay, so alpha equals 0.01. So when I draw my normal probability distribution, the right tail will have how much? Half of that. So that's going to be 0.005. And the left tail will have half of that, so 0.005. Okay, so the z-value here, okay, is going to correspond to the z-value here is going to be a marker such that the area to the right is 0.005 and the area to the left is 0.995. How do I get 0.995? Because area to the left of the z and area to the right of the z should equal 1. So if this is 0.005, this has to be 0.995. Okay, and I know that the middle probability is 0.99. So 0.99 plus the left tail is area to the left of z. Once you know the area to the left of a z-score, finding z-score is really easy. You can look it up into a z-table. So you can find z-table online or at the end of your textbook. And the z-table lists, v-values along the margins and probabilities in the middle of the table. Okay. So in the middle of the table, you look for 0.995. And whichever value is 0.995, you can read the z value from the margins of the z table. If you don't know how to look up a z table, you can, Google a tutorial or review your stats notes. I don't think you should be looking at z tables at all, so I'm not going to teach you. I think it's a waste of time because we can easily use Excel to convert the probability of 0.995 to the corresponding z-score. So this probability can be converted to the corresponding z-score with just one command in Excel. That command is like this. It goes like this. You type equal norm dot, this is n, okay, norm dot s dot inv, and in brackets you give it the probability. This will be 0.995, and this would give you the z-score. So let's do this. Okay, so my alpha is 0.01, okay, which means left side of z, the probability will be 1 minus alpha over 2, okay, or 0.995, just like we discussed. So my z-score, okay, is simply norm dot s dot inv, and in brackets I pick this probability to the left of the z value, and lo and behold, my z-score is going to be 2.57583. So now I have everything I need to find the upper and lower control limits. So I can go, I can look at the formula in the slides. It's just p bar plus z times the sigma, and p bar minus z times the sigma. Okay, so I take p bar plus z times the sigma. That is my upper control limit, and the lower control limit is going to be p bar minus z times sigma. Okay. Notice I got a negative value, so that's going to be rounded to 0 because you can't have a negative probability. It's impossible. So my answer is going to be this and this. So we can test it out, 0.15183. So I think it tells us to round the answer to 3 decimal places. In Excel, you can round easily using these buttons, which move the, move you right or left. So you move it here to 3 decimal places. It's 0.152. Okay. And it tells you if you get a negative limit, it's going to be 0. Okay, so 0.152 and 0, and that was correct. Okay. Now it tells us that for the last 3 weeks, what can we conclude? So we want to look at data of 9, 4, and 6. Okay. And so basically what you want to do is for the last 3 weeks here, you want to calculate the proportion of each week. So 9 divided by 64 is 0.14, 4 divided by 64 is 0.06, 6 divided by 64 is 0.09, and you want to compare these values with the upper and lower control limit and see if they are within the control limits or not. Okay, so in other words, to show you, pictorially, this is what we are doing. So we have 2 control limits. My UCL, upper control limit, is 0.152, and my LCL, lower control limit, is 0. So day 13, sorry, with 9 absentees, I'm at 0.14. So 0.14 is less than 0.15. So I'm going to be somewhere here. Let's use a different color, somewhere here. Okay. And then day 14, I'm going to be 0.06. So I'm going to be, somewhere here. And then the last day, 0.09, may be somewhere here. So all 3 values are within the control limits. Nothing is exceeding the control limits. So we are in control. Okay. All sample proportions are within the control limits. So the process is in control. We'll select this option, and voila. So that problem is done. Okay. So if you look at the working example in the book, once you find P bar, or even if you don't find P bar, actually the book examples do give you data like this. Only in the CPK problem, the booked example don't give you the metrics. They give you the metrics and you don't have to calculate them, but in the P chart problems, you're often given data like this, and you have to find P bar and sigma P bar, right? And then they give you the type 1 error probability. This is type 1 error probability, which is your alpha, and then you can convert it to a z-score by first finding the area to the left of the z-score, because you're going to put half of alpha to the right of z-score, so the rest of the area would go to the left of the z-value, and then you convert it to a z-value using this function. Okay. Okay, let's do the second problem. So the second problem we're going to do is this one. We have to find process capability metrics of CP and CPK, and we're given some data. So again, we're going to select this button, do Control C, and come to a new Excel worksheet. Okay, and we're going to paste the data here. Okay. So remember that we have some labels for the data. Okay. So we have 5 samples, 1, 2, 3, 4, 5. Each sample has 8 values. However, remember that CP, CPK are not updated incrementally like a process control chart. With the process control chart, every some time you take a sample and you plot it on the control chart. So over time you get some pattern like this. But CPK and CPK, you might compute them periodically, but if the process variation is in control, these should not be moving. They should stay the same value. So you don't really need to find sample 1 and then update the value in sample 2, then update the value in sample 3. So basically for this question, all of this data is just one big sample. Okay, so 8 times 5, you have 40 values. They're just one big sample. Because you're not going to do sample 1, okay, this is what's happening, sample 2, this is what's happening. That is for control charts. And the reason the book is giving you the data like this is because they feel you're kind of used to the control chart format of the data, right? They could have just as well listed the 40 values in one column. It's the same thing, okay? So for CPK, right, we can look at the formula for CPK in the slides. Is right here. CPK is the minimum of 2 calculations. So we calculate 2 things first. One of them, both of them actually use X bar bar, the mean of the means. This is the mean of the sample means or the mean of the whole data, and then you need the process variability. How much does the values in the process vary, which is the standard deviation sigma. Okay, so X bar bar is just the average across all this data you have. Okay, you can also find average of sample 1, which will be like X bar 1, right? So X bar 1 will be the average here, and then X bar 2 would be the average here, and so on. And you will find 5 X bars, and the average of the 5 X bar, 8.555, is the average of the entire data set. But you don't have to do it in these 2 ways. You can just do it directly. Just do equals average and find the average of all the numbers. Okay, and then you need sigma, which is the standard deviation in the data. So standard deviation in Excel is just stdev.s. Okay, you don't want to use .p because .p is when you have every possible value observed and in front of you for that process or that context. We don't. There's, the process runs for more than just 5 samples. This is just a sample. So .s stands for sample. So always use .s and then select all the values, and that is your sigma. Okay. Then we need upper spec and lower spec. These are specs from the customer, how much tolerance we have in making this product. We are 8 plus minus 3 millimeters. So on the upper side, we can be 8 plus 3 or 11 millimeters. On the lower side, we can be 8 minus 3 or 5 millimeters. Okay. Okay, now we have everything to calculate CPK. So the first CPK1 is going to work with the lower spec. So we take X bar bar minus, let me open a bracket. So open a bracket, X bar bar minus the lower spec, and then divided by 3 times the sigma. And you want to put 3 times sigma in brackets as well. Otherwise, it will just divide by 3 and multiply by sigma. You want to divide by the whole thing, 3 times sigma. So you can use, parentheses like this. I kind of use brackets and parentheses as synonyms, although they're not. But please bear with me. So when I say brackets or parentheses in Excel, I just mean these Shift 9 and Shift 0 keys that you can type here. These just tell Excel in which order to do the operation. So it solves the the top part first, solve the bottom part, then divide the two numbers because this is the division operator. Okay. Okay, now you find the second value of CPK2. That's going to be based on the upper spec. So you're going to do upper spec minus X bar bar. So it's the opposite. Before you did X bar bar minus lower spec, now you do upper spec minus X bar bar, divided by 3 times sigma. And how do I know it's upper spec minus X bar bar and not X bar bar minus upper spec? The formula tells you that upper spec minus X bar bar, not the other way around. And an easy way to remember that is that the numerator must always be positive. And so if you were to do X bar bar minus upper spec, you'll get a negative number. So you're not going to have a negative numerator in these calculations. So then the real CPK is just the minimum of these two values. So you can just see this is the minimum, so that's your answer. Or if you want, you can use the equals min function to select the minimum value. Okay, so that is your answer. Okay. And then the next part of the question asks us to calculate CP. CP is even simpler. Again, the formula is given in the slides. Upper spec minus lower spec over 6 sigma. CP does not care about X bar bar at all. So you do upper spec minus lower spec divided by 6 times the sigma. Okay. And that's 1.102. So that is the second answer. Now, probably it's going to ask us to put answers to 3 decimal places. Yep, it does. So I'm just going to use this button to round it to 3 decimal places. Or you can do it mentally. So 0.898 and 1.102. Okay, 0.898 and 1.102. Okay. Now both these values are below. So this is below 1.33. This is below 1.33. The process is not capable, right? In the text, the question could specify that the target level is. So the target performance or level or capability is 4 sigma. That means 1.33 CP/CPK. Okay, if target performance is 3 sigma, that means 1.0 in CPK and CP. Okay, if target performance is 6 sigma, that means 2.0 in CPK and CP. And you have a slide that tells you these levels. So you always compare with your target level when you're deciding whether the process is capable or not. If no target level is given, the default that we're going to use is 4 sigma, which is 1.33. Okay. So in this question, I believe no target level is given. So we're going to go with the default of 1.33. Since both values are below 1.33, the process is not capable. It's going to produce a ton of outer spec parts. So it's not capable because there are too many parts outside of the allowable tolerances. Because both CPK and CP are, excuse me, are too small. Okay. Now, if, let me give you another example. Let's say you got a CPK of the same, 0.898, okay? But let's say you got a CP of 1.34. Now CP is above the target level of 1.33, but CPK is not. In that case, what it's telling you is that your process standard deviation, the sigma is good. Your process is very tight. It doesn't have a lot of variation, but it's not centered properly because CP does not care about centering, CPK does. So if CPK is too bad and CP is good, that means centering is the only problem. If you fix the centering of the process, if you fix the X bar bar to be in the middle of the upper and lower spec, that'll solve the problem. And so you would say, okay, the process is producing defects because it's not centered properly. That'll be the right option. Right? But when both of them are bad, CP, CPK are both bad, then the process is just it's not centered properly and the variability is bad. Everything is bad. And so you'll pick this option that there are too many parts outside the allowable tolerances. Now, again, in the slides and the lecture, I do explain, especially the lecture, I explain, when I cover these 2 slides, what does it mean when CP is okay, but CPK is not okay, and how to interpret that. So refer to the lecture for more details on that. So that's all for this video. Hopefully with these two worked examples, you will feel more comfortable doing problems like these.